This is a quick series on levers, pulleys, inclined planes, torque, and angular momentum. With the exception of angular momentum, these should be things that you learned in middle school in integrated physics and chemistry, but I find often students did not learn them or have forgotten them. So it's a quick study because this is something you definitely need to know as a physicist. Let's start with the idea of what a machine is. A machine is something that increases, multiplies the force. What it does not do is change the work, because if you put work into something, you get work out. Generally, you get less work out than you put in because you have friction and other forces that work against you, so you don't get as much work out as you put work in. But let's ignore those in this discussion. The point is you can never get more work out than you put in, but you can get more force out than you put in. So you can have a force multiplier, but you cannot change the amount of work. Remember when we talked about work before, we said work is the force times distance. So the work in, force 1 times distance 1, would have to be the work you got out, force 2 times distance 2. And that is the whole idea and concept behind a machine, and also behind the entire concept of levers, pulleys, inclined planes. Let's start with an inclined plane. We have a parallel surface, and here is the inclined plane. It is most often defined perhaps by the angle at which the slanted portion, the inclined portion, comes up, or you might be given the height, or you might be given the length of the plane itself. And as you know, sometimes this is called D, sometimes it's called even R, sometimes it's called S. So all of those variables are sometimes used, but in any event, it is the length of the ramp itself. This portion down here is really never used in the calculations, so we don't use that portion. So we're going to talk about the ramp here, the height, and the actual angle that the inclined plane makes. So let's go back. What did we say a machine was? A machine is something that multiplies the force. So it is a force multiplier. So we want to define this in some way. So we define the actual force multiplier by something called the mechanical advantage. So the mechanical advantage is going to be the force out over the force in. So if you get more force out than you put in, you have a mechanical advantage greater than 1, which sometimes is often desired, but you might not desire that and actually want it to be less than 1 for reasons that you will see in a few moments. So the inclined plane is a force multiplier. It is a machine, a simple type of machine, and it gives you a mechanical advantage. The mechanical advantage is very easy to figure for an inclined plane. The mechanical advantage is simply going to be the length of the sloping part divided by the height. Now let's look at some relationships, just so when you work problems you think about it. If we had the angle theta, we could say the sine of theta is equal to h over L. So therefore the mechanical advantage would be 1 over the sine of theta. Don't confuse this with the arc sine. The arc sine is not 1 over the sine of theta. The arc sine is an inverse function and has nothing whatsoever to do with 1 over sine theta. We do write the arc sine as sine minus 1 theta, but that is a notation. It is in no way equal to and has no relationship whatsoever to 1 over sine theta. So keep that in mind. I'm going to erase this so there's no confusion over that. So now let's suppose we have the inclined plane again. And Let's give the length here of 15, and whatever the units are, meters or feet or whatever, and let's suppose the height is 5. So the mechanical advantage will be 15. If we want this to be meters, that's fine. The height is 5 meters. The meters cancel out because mechanical advantage has no units, and so the mechanical advantage of this inclined plane is 3. Now, what does that mean to have a mechanical advantage of 3? We'll go back to what we said. The mechanical advantage is our force multiplier. We should get a force multiplier of 3. So let's suppose a box weighed 100 pounds. Then how much force, ignoring friction of course, does it take to push it up the inclined plane? Well, that's where our mechanical advantage comes in, because the mechanical advantage is 3. So if we push this with a force of 33 1/3 pounds, a mechanical advantage would say that's as if multiplied by 3, that's as if we were pushing 100 pounds. So we easily calculate that, ignoring friction, we could push this box that weighs 100 pounds here up the inclined plane with a force of 33 1/2 pounds, because the mechanical advantage is 3. We only have to push with 1/3. Don't get this mixed up and think you have to push with 3 times the force. Remember, the mechanical advantage is force in divided into force out. So I push with 33 1/3, I get 100 out, mechanical advantage of 3. Once again, let's suppose we have a box that weighs 60 newtons, have the same slope that we had, 15 meters up the ramp, 5 meters here. Let's talk about now how much work is done, because what I said before was that the work doesn't change. You still have to do just as much work. So let's see, how much work would I have to do if I took the box and I just lifted it to the top of the hill? Well, the work is the force times distance. So the work up the inclined plane, lifting straight up, would be 60 newtons, the force, times 5 meters, the distance, would give us 300 newton meters, which would be joules. Let's look at the work pushing up the inclined plane. What's my force? Well, we've already calculated the mechanical advantage is 3, so the force up would be 20 newtons, because it's 1/3 of 60. 3 times 20, our mechanical advantage gives us 60. So our force is 20 newtons times 15 meters, and we get 300 joules of work. So we do the same amount of work going up the inclined plane as we do lifting it straight up. So as we said in the beginning, assuming there is no friction, the work we get out will equal the work we put into it, or certainly be less than it, but regardless, without any friction or any other forces. So we don't save on work. How is it then that we get a mechanical advantage? We get it because we are moving it through a longer distance. We push with less force, but we must push through a longer distance. That's equal to more force, but through a shorter distance. So the work is the same, but the mechanical advantage and the force multiplier are not. Now let's look at a couple of simple problems. Suppose we have an inclined plane that makes an angle of 23 degrees with the horizontal. What is the mechanical advantage? Well, to get the mechanical advantage, we need the force out divided by the force in. Well, if our box weighs 100 newtons, that's our force out. We're lifting 100 newtons. How much force would we have to put into it to get it up the inclined plane? Well, the mechanical advantage of the inclined plane is going to be the length over the height. We don't know the length of the height, but we know that the sine of 23 degrees is equal to 0.39. And that's equal to h over L, if this is h and this is L. But I don't want h over L, I want L over h. So I have 1 over 0.39 and that's equal to 2.56. So the mechanical advantage is 2.56. Okay, so the question comes then, how much do I have to push on this box to get it to go up the hill, assuming there's no friction, of course? Well, the mechanical advantage is 2.56. So I take the 100 pounds, or 100 newtons, divide it by the mechanical advantage of 2.56, and I get 39.1 newtons, and that's the force that I would have to push it up the inclined plane, 39.1 newtons. 39.1 times 2.56 gives me 100.